In section 19, we'll be looking at defining a new function called the logarithmic function. And the logarithmic function ends up being a response to the exponential function, as there is a need for an inverse of the exponential function. So this first example is going to introduce a inverse to a function that we've already seen, which is the exponential growth. So we have f defined for us, given by f of x equals 2 raised to the x. The domain will be all real numbers, and we are expected to graph both f as well as f inverse on the same Cartesian coordinate plane. The way that we graphed f of x equals 2 to the x in section 19 was by first making a table. And I'm going to take that same approach here with this example because it's going to give us a nice ground up approach to being able to create this new function, which is the logarithmic function. So we'll start with some x values of, we'll just pick -2, -1, 0, 1, and +2. And then when we plug those in to our function equation, we will get the f of x values to be 1/4, 1/2, +1, +2, and +4. And since we've already got that table completed, we'll go ahead and graph these points. And when we did this in the previous section, we had recognized and observed that there was a horizontal asymptote sitting right on top of the x-axis, which was located specifically at y equals 0. And then the graph would be increasing, going from left to right. And this is what we called exponential growth. And for us, this is f for this example. Now for f inverse, we had looked at this in section 17, talking about the one-to-one and inverse functions. This function f that we just graphed would definitely qualify as being a one-to-one function. It passes both the vertical and horizontal line test. So there is no problem with us creating a inverse. So we're going to say the first step that we were doing before was take out the function notation, replace it with y. And then to create the inverse, all we have to do is literally switch the x and y. And that presents us with x equals 2 raised to the y. Now back in section 17, we would always take the equation and then solve it for y. So the goal was eventually to get to y equals something. The original inverse that we created, just from the switching of the x and y, this is what we called the implicit form, or the implicit inverse. And then our goal was to eventually get to the explicit inverse. And once we get to the explicit inverse, then we have the ability to call this f inverse of x using the inverse notation. But there's a big problem here. We don't have the ability to be able to solve this for y. This is not like a squaring function or a square root function or a linear function or a polynomial. I mean, those are all things that we can take the inverse of and easily get them into the explicit form. We don't have such tools for us to be able to do that with this. So the best that I can do then to be able to get the graph completed, because it doesn't say that I have to have the equation, it just says to graph f and f inverse. The best that I can then do is take the points that we already have for f of x and use those to create f inverse. So f inverse is going to take the x's and the y's from f, and it's going to switch them. I mean, that's what we did to try to work on the equation, just to switch the x and the y. So that means that the 1/4, 1/2, 1, 2, and 4 are going to be the new x values, and then -2, -1, 0, 1, and 2 are now going to be the y values. I'm going to use a different color to graph this. And let's see, 1/4, -2, 1/2, -1, 1, 0, 2, 1, and then 4, 2. And the curvature is going to be a little different than the original function. Obviously, since it's the inverse, it should be different. But we'll notice that it is still increasing though, but we don't have a horizontal asymptote. Instead, we have a vertical asymptote located specifically at x equals 0. So when we end up switching the x and the y, not only do we switch the x and the y for all of the ordered pair, but we also have to switch the x and the y on the equation for the asymptote, which is why it goes from being horizontal to then being vertical. So you can see that the red line now represents what we would call the inverse of f. And back when we talked about inverses in section 17, we had said that there was this line y equals x that represents the line of reflection for these two functions. If they are truly inverses, then you will be able to take your page and fold on that line y equals x, and you wouldn't be able to tell the difference between the two graphs. And that's exactly what happens here. So we don't quite have the ability yet to get to the explicit inverse equation, but that's going to be what we're looking at and investigating here in section 19.